Hello everyone. I'm happy to meet you at Swift Tokyo 2024 and talk to you about parallel socket communication in Swift. My name is SHIMOTORI. I work as an iOS engineer at LY Corporation in Tokyo. Additionally, I do volunteer work at some tech conferences. Today, I'm assisting Trace Swift with their recording tasks as a member of Droid Kaigi committee. I've learned a lot by organizing tech conferences. For example, what network architecture is effective for Wi-Fi and live streaming? I studied network through not only textbook, but also programming. Network technology is essential for applications too. The standard libraries enable communication over the internet without knowledge of network. Even so, knowledge of network is helpful for comprehending the lower layers and the standard libraries. Today, I will introduce you to network through programming. As an introduction, let's try simple communication without data transfer methods defined by foundation, such as URL and URL session. Of course, we will not use HTTP libraries commonly used in application development. Let's get down to the main topic, parallel socket communication in Swift. I will share the excitement of network programming in Swift. What is socket communication? Socket communication is a type of inter-process communication. Inter-process communication, IPC, is a mechanism for exchanging data between multiple processes. IPC enables multiple processes to collaborate, work together, and access common resources effectively. When processes on the same network need to exchange data, that's where socket come into play. A process can send messages to others on different hosts over a socket. POSIX defines the interface for sockets, and both macOS and iOS roughly conform to the POSIX standard. We can experiment with socket using the familiar environment provided by these platforms. Socket can send various types of data. This time, we will try implementing a ping program. A ping program works with a very simple logic, which makes it perfect for beginners to start learning socket communication. Let's take a look at the output of the standard ping command. This message contains byte count of received message, IP address, ICMP sequence number, TTL, and elapsed time. You are usually interested in elapsed time to check latency. Other parameters provide information about how and what data returned to your machine. In fact, the ping command sends a short message to a host every second. The message has a fixed format and includes a sequence number. If there is nothing wrong with your network, the host will respond with a reply message. The reply message also follows a predefined format and includes the same sequence number. If a network failure occurs, the ping command will display a timeout error message. To keep things simple, let's start by implementing a serial ping program, not parallel. This will send at most one message at the same time. We need an async function like this for such ping program. This method needs identifiers, sequence number, and address. You can pass any value to identifier. Sequence number is an incremental number for each call. Address takes an IP address as a string type. This method returns a result result that includes elapsed time to receive a response, and it may throw a timeout or internal error. Now that we've decided what to implement, let's dive into socket communication in Swift. There are 3 tasks to implement the function. The first is to create a socket. The second is to decode and encode messages. You must follow the ping protocol specification. The third is to use system calls to exchange messages with a destination host. Let's start with the first step. There are different types of sockets. This time, we will use a datagram socket to send ping. A datagram socket is typically used for UDP connection. Unlike TCP, it doesn't establish a logical transmission path to the host. It has few procedures to increase reliability, such as sequence control or retransmission control. A destination host receives a message from your machine suddenly. A datagram socket and a ping program share a common feature, sending message without notice. Therefore, this socket types is suitable for sending ping messages. How can we use sockets? Sockets are treated much like files. In Swift, you can use a socket simply by importing foundation. First, the socket system calls returns a positive int32 value. This is a file descriptor pointing to a created socket. This positive value allows messages to be exchanged. Socket system calls require this int32 value. When communication is complete, use the close command to close the file descriptor. The lifetime of the file descriptor is until it is closed. However, we still have the int32 value. We may accidentally execute additional system calls using this value and cause a runtime error. To avoid such errors, you should wrap an int value with a non-copiable structure. This file descriptor is a self-defined structure and conforms to non-copiable. This ensures that the lifetime of the file descriptor is the same as the lifetime of the constant. This allows the Swift compiler to detect that we are using an unavailable file descriptor by mistake. If you are interested in this structure, please refer to the article about non-copiable in Swift evolution. Next, an encoder and a decoder of the ping message. If we are implementing an echo client, we can just pass data to a socket. But to send a ping, we need to prepare binary data in the ping format. Let's look at how to create message data. This is a byte string of a ping message. When a server or a network device receives this byte string, it recognizes that the ping reply is requested, and then sends a reply back to a source process. Sockets functions require a data type object, so you need to prepare a binary string as data type. Writing binary data by hand is not practical. What is the format of this data? Is there a simple way to prepare a ping binary message? Here's the format of outgoing ping message. It specifies which bits represent which parameters. For example, the sequence number is a 16-digit number from the 49th to the 64th digit. The sequence number in this binary string points to 5. Structure helps you to encode and decode the ping message. Structure simply puts its property data in order in memory. You can get the binary message for ping by reading binary data of structure. But you have to keep in mind that Swift stores data in little endian formats, but network treats data in big endian formats. TCP/IP adopts big endian. If you want to write ping message binary data using a structure, you must swap bytes manually. In Swift, integer types can change order their bytes. Their big endian property returns a new integer value that is swapped by LLVM byte swap instruction. What about coding? As explained later, you can obtain received binary string as data type. This binary string includes the sender's IP address and TTL, which are necessary for the ping output. To decode binary ping string retrieves the structure from a data object using unsafe row buffers load method. These integer values are in big endian format, so it is necessary to manually swap if their lengths are 1 byte or longer. After preparing the message data, use system calls to send and receive messages. System calls are provided as C functions. If you are familiar with C interoperability, you can use them without issue. These are system calls to send and receive messages over datagram sockets. Send to send a message, poll to poll a message, and receive from to read a received message. The poll system call has a timeout parameter. If the datagram socket receives a reply message before the timeouts, you can return success. If timeout error occurs, you can throw it. There are two major differences from Swift methods. They require unsafe values and block until processing is complete, since they are not asynchronous. This is sent to system call. With unsafe bytes and with unsafe pointer enable C interoperability. These methods provide unsafe values as closure arguments. The scope of these closures represents the lifetime of unsafe values, and they prevent us from accidentally referencing discarded pointers. These closures are nested, but it is a safe way to handle unsafe pointers. These are functions to receive a reply. Do not call these functions in the main thread. Moreover, the receive from function takes a pointer to data and places a received message in it. So you should also wrap these system calls too. You can call them as usual by making them asynchronous function that returns a data object. That's it. These tips can help you implement a serial ping program in Swift. We have confirmed that sending and receiving messages is simple, even with socket communication. We can define an async request method using a socket in Swift. The remaining tasks are to call the ping function every second and display the results in the user interface. The ping function can work with a clock ticking every second, such as a publisher or an async sequence. When the datagram socket receives replies, you can pass them to your preferred data binding, and then display results on the command line interface like the standard ping program, or use Swift UI to build cool views. The created ping program just sends a message, waits for a reply, and decode it. But what if you want to make it more sophisticated? For example, if you want to monitor multiple hosts, it would be useful for you could send to all hosts at once. Such feature requires sending a ping parallel. Why do we need such feature? Of course, the standard ping program is useful to check latency from your PC to a game server. However, to monitor a complex network environment such as a tech conference, the standard ping program is inconvenient. monitoring heartbeats requires running a ping program for each device. For this reason, I usually use an open source ping tool called DetNam to monitor a conference network. This tool is coded in Python. It sends ping to multiple devices and displays the results in a text user interface called newcurses. How can we implement this program in Swift? The system calls I introduced are executed atomically. Sockets send message data accurately even if you send them frequently in parallel processing. However, receiving reply message can pose some problems. A datagram socket doesn't establish transmission path, which means it receives all messages from any host and cannot sort received messages by senders. In this case, datagram sockets cannot measure timeout by polling. The poll function returns success when a message arrives from any host. Application layer should sort received message and handle timeout instead of sockets. Thus, the data flow from a datagram socket to ping module should be a single stream. Only one datagram socket receives all message, and then Swift measures timeout instead of the poll system call. Specifically, this program continues polling with a single datagram socket while it is waiting for replies. Implement a timer on application layer and set it at the same time as sending a ping message. If its reply arrives before the timer indicates timeout, mark the ping request as successful and cancel the timer. If the timer expires, mark it as timeout. So we have two additional tasks to implement a parallel ping program. The one is sorting reply message from a socket. Specify their paired ping request by identifier and the sync number. The another one is timeout error. Set a task that triggers timeout after 1 second sleep. If its reply arrives, cancel the task. If no reply arrives within 1 second, the task will fire timeout error. Fortunately, as you know, Swift concurrency is powerful enough to implement them. Also, combine can be used to easily handle results, including timeout and internal errors, and pass them to UIKits, AppKits, or Swift UI. Please let me add information about newcurses. DetNam uses newcurses. There are two problems with using newcurses like DetNam does. The first is that newcurses is not thread safe. Newcurses doesn't work well with parallel processing. The second is that newcurses works with an opaque pointer. In this case, this pointer is a kind of resource that has a masked state about whether it is available or deleted, similar to a file descriptor in a socket. However, these are not problems for Swift. We know Swift has actor and non-copyable. They help us to operate newcurses safely. How was it? I would be happy if you could realize that socket communication in Swift is not as challenging as it may seem. Let me sum up my talk. Socket communication is unfamiliar to us, but you can easily give it a try using Swift. Swift helps you to use sockets safely and learn network programming and system programming. I hope you will try socket communication. I will put this slide and some documents on the internet. If you want more details, please see the reference list at the end of this slide file. Please feel free to ask your questions and provide feedback in Ask the Speaker. During this event, I will be at either the recording booth or a Light Corporation sponsor booth. I am excited to talk with you. Have fun learning socket communication and new things with Swift. Thank you so much for listening.